Organic chemistry often appears as a chaotic jumble of letters and arrows, yet every transformation is governed by a singular, predictable goal. Molecules are in a constant, relentless pursuit of a lower, more stable energy configuration. This reaction coordinate illustrates the thermodynamic trade-off. A molecule breaks a weak pi bond to facilitate the formation of two incredibly strong sigma bonds. The resulting exothermic energy drop drives the process forward. The electron-rich alkene inherently reaches out to react with a nearby polar molecule. We track this energy release through electron movement. A curved arrow flows outward, showing the alkene weaponizing its pi electrons to capture the partially positive hydrogen. This creates a positive carbocation intermediate. The bromide anion then uses its lone pair to attack, forming the neutral product. When the starting double bond is perfectly symmetrical, the outcome is uniform. However, introducing structural asymmetry creates a specific chemical choice. Consider propene reacting with hydrogen bromide. We have one hydrogen atom to add, but two distinct carbons on the double bond to choose from. The reaction pathway is dictated by the stability of the intermediate. Path A leads to a primary carbocation, which is highly unstable and shakes violently. Path B produces a secondary carbocation, which achieves a much smoother, lower energy state. This secondary carbocation is stabilized by hyperconjugation. The adjacent carbon-hydrogen bonds share a fraction of their electron density with the empty orbital, spreading the positive charge across more of the molecular framework. This preference for the most stable intermediate pathway is codified as Markovnikov's rule. The bromide targets the secondary position, resulting in the major product 2-bromopropane. Predict the major product of 3-methyl-1-butene reacting with HBr. Many students fall into a trap here. The reaction begins with the formation of a secondary carbocation. However, notice the highly substituted carbon sitting right next door. Because the molecule seeks the lowest possible energy state, it spontaneously reorganizes. A hydrogen atom migrates from the adjacent position in a 1-2 hydride shift, moving the positive charge to the tertiary carbon, which is even more stable. The bromide then attacks this tertiary site. Anticipating these skeletal rearrangements is essential for accurately predicting the final product in complex organic systems. Chemists can intentionally reverse this outcome by introducing peroxides into the reaction. The peroxides shift the mechanism from a polar ionic pathway to a free radical chain reaction. This places the bromine on the least substituted carbon, the anti-Markovnikov position, without the risk of carbocation rearrangements. These addition principles expand into the field of polymerization. In chain growth processes, thousands of vinyl monomers link across their double bonds in fractions of a second, allowing for the industrial-scale synthesis of materials like polyethylene. This summary matrix clarifies your options. Standard addition proceeds through a carbocation and follows Markovnikov's rule, but requires a search for potential rearrangements. Radical addition utilizes peroxides to reach an anti-Markovnikov result, bypassing the ionic pathway and the possibility of skeletal shifts. Tracking the flow of electrons through these specific pathways provides a reliable framework for predicting reaction outcomes across the entire field of organic synthesis.